Okay, so tonight we're going to start our introduction to the metric system. So what we should be able to do here are perform various unit conversions using the metric system. Okay, so when we're looking at converting things like micrograms to grams to kilograms, you should be able to do those various kinds of conversions. Now, if there are conversions that use the US units, I will give you those conversions. Okay, so usually on the tests, I would only give the US conversions. I do not give the metric system conversions. So if we were doing this in class, I would say you would need to know the metric system conversions in order to do the problems. Okay. All right, so we have a set of base units. Now, the metric system is a much more elegant system of units. It is far above and beyond, vastly superior in every conceivable way to the system that you're probably used to here in the United States. Okay, scientists operate on the metric system for the most part, by and large. My household runs a 100% metric system in my house, so I make everybody use the metric system around the house. So we don't, I try not to use any of the US units because they are terrible. And so once you know the conversions of the metric system, they work whether you're talking about length or mass or time or electric current or temperature or luminosity or the amount of substance. It doesn't matter. The metric system conversions are the same across any of them. Once you know the prefixes, the conversion factors between them are the same, right? It is not like in the US unit where you have, there are 12 inches in a foot and 16 ounces in a pound. 12 and 16 are not the same unit if I change from length and weight. Whereas if I go from a kilogram to a gram, when 1 kilogram, there's 1,000 grams. In 1 liter, there's 1,000 milliliters. The units are the same across the various things, and so we generally will work from the base unit or the fundamental unit for most of these units, and then the conversions are in powers of 10. Okay, so these are our base units. Now the only one here that usually catches people is the gram. Okay, is that when we generally measure things, the gram is kind of where we establish our base unit. But technically, from the metric system, the kilogram is the base unit for mass. Okay, so, but we generally don't work, at least in chemistry-wise, we generally don't work too much in kilograms, so a lot of it tends to be more in the gram-wise, and so when you see my base conversion unit, really the gram is what I'm talking about for some of the conversions as we memorize the different terms. Okay, so we have length is a meter, mass is a kilogram, time is in seconds, temperature is in Kelvin, amount of substance is a mole. We're not really going to talk about electric current, but that's an ampere. And luminous intensity, again, we're not going to deal with as a candela. All right, so in most books, and I don't know how many times I've been teaching this and I never end up fixing this slide. There's also a giga in here that's in between a mega and a tera, right? In most books, you have this slide. Now, the prefix symbol, okay, is going to be the same whether we're talking about grams or liters or moles or time, it doesn't matter, okay? These prefixes are going to be the same across the board. The conversions here, right, are really, there's one of two ways that you can see this slide. Now, this slide is generally presented in a way such as if we're looking at 1 meter, okay, so they're saying that there is 0.01 meters in 1 centimeter. So here, this slide is looking at how many of the larger units fit into the smaller unit. Okay, so they're saying 1 centimeter is 0.01 meters. Okay, now This is generally not how I work on the metric system. When you see me do practice problems, which we will try and do here, I don't usually go with this metric. Okay, I usually use this particular slide. Okay, now the only difference of these two slides is this second slide is like saying I can fit 10 people in this room. This previous slide says how many rooms can I fit in a person? Okay, so you see the difference is it's how many of the larger unit fits into the smaller unit, or how many of the smaller units make up the larger unit. Okay, now most people, at least I would think in my experience, are able to understand a buildup of units. So here I kind of recalibrated the base unit as the main unit. And so for most of these, the smaller units, so we want to know how many of the smaller units make up the larger unit, right? So now 1 meter, okay, is a base unit. Meter is the base unit. There are 100 centimeters. Okay, now this doesn't functionally change anything, but you have to pick one of these. Okay, you have to pick one of these slides to go. Okay, you can't do both. You got to pick one, all right? Because it makes a difference when you do the problems. Okay, so you just pick one and stick with it, and then you'll be fine. Okay, but this particular slide here is the slide that I generally use when I'm doing practice problems. Is I look at how many of the smaller units make up the larger. So if I have a micrometer or a millimeter, right, there's 1,000 millimeters in 1 meter. There's 100 centimeters in 1 meter. There are 10 decimeters in 1 meter. And then here, now the base unit is no longer the smaller unit, the larger unit. Now there's 1,000 meters in 1 kilometer. There's 10 to the 6 meters in 1 megameter. Okay, there's 10 to the 9th meters in 1 gigameter. Okay, so this is how many of the smaller units make up the larger unit. All right, so this is more how we would do if we were looking at things like there's 12 inches in a foot, right? That's generally how people would do the US unit. There's 12 inches in a foot. Versus this slide is how many feet are in an inch, right? How many feet are in an inch is what this slide is telling us. Okay, versus how many inches are in a foot. Okay, how many feet are there in a yard? Okay, versus how many yards are there in a foot. Okay, so that's the difference of these two slides. All right, some US conversions that are handy to have. Now, it's important that we should be fluent enough in some conversions that we can do conversions on the fly when we go to other countries. Because for the most part, most of the rest of the civilized world uses the metric system. Okay, we're one of the few. There's probably 1 or 2 other backwater countries that use some busted unit like this. Right, but for the most part, everyone else uses the metric system. So good units that are good to have memorized is there's 2.54 centimeters in an inch. Okay, there's about 2.2 pounds in a kilogram. There's about 1.6 kilometers in a mile. All right, and there's about 3.7 or 3.8 liters in a gallon. Right, so this is one that you see a lot, especially if you travel overseas and they're buying gas by the liter. And so you see the vast difference in price because they're paying by the liter versus the gallon, right? So again, on the test, I would give you these conversions should you need them. Okay, you wouldn't have to have these memorized, but again, this is something it's good to have at least if some of these memorized so that you can make these kind of conversions on the fly if you need to. Okay. All right. So let's talk about mass. All right, so here we're just going to break down each one of the units. Again, the SI unit here is the kilogram. All right. Mass is the amount of matter present, but for the most part, we use it synonymously with weight. Okay. Weight and mass are not strictly technically the same thing. Okay. If I go up to the International Space Station, I don't suddenly stop having a mass, right? My weight, I become weightless because weight is a function of gravity. Okay. You may weigh a different amount on the moon or on the International Space Station, but your mass is still there. The amount of stuff that you are made up of is still the same, right? So again, the SI unit is a kilogram. Common unit that is good to memorize is there's 2.2 pounds per kilogram. Okay. For length, our SI unit is the meter. Okay. A good unit to have memorized that we will use often is that there are 2.54 centimeters in an inch. Okay. This is an exact value. All right. So you can see kind of a slight difference in the meter versus the yardstick. Right. Volume. So if we were in the lab, so this would be one of those times where if we were in the lab, we could look at some of these different pieces of glassware. Obviously, we have a variety of different kinds of glassware, especially if we were in the lab, in order to measure things like volume. So the SI unit here is the cubic meter, since length is our meter. Or it could be a liter. I guess we could, also use the liter too. So there, the volume measurement is generally in liters if we're looking at liquids, and then if we're looking at solids, it generally tends to be in centimeters cubed. Okay, so it's a little hard to do volume in centimeters cubed or meters cubed if your flask is round. So if you have a dimension where you can measure length, width, and height, then you can get the volume. But generally, we don't have that in some of these pieces of glassware where we have an easy way of measuring that. This is why you generally have two different kinds of volume cups in your house, right? So you have a liquid volume one, right? That's like the little cup, and then you have little scoops, right, for the solid. So you have two different measuring apparatus for your volume. The one thing to keep in mind here that helps for converting these units is 1 milliliter is 1 centimeter cubed, or a centimeter cubed is also a cc. Okay, so the medical units of the cc is the same as a milliliter, right? They're talking about a cubic centimeter, right? So we'll have some dimensional unit conversions, and so this is a good one to make where we convert from dimensional units into fluid units. All right, temperature. Okay, so this is probably a new scale that many people may not be familiar with, which is the Kelvin scale. Okay, so most everybody's familiar with at least Fahrenheit and Celsius. Okay, we will not use the Fahrenheit scale ever. Okay, there is a conversion from Fahrenheit to Celsius, but I probably will not give you any questions. I am going to assume the Fahrenheit scale does not exist. Okay, so our Celsius scale sets from our water, here, freezes at 0 and boils at 100 degrees, whereas on our Fahrenheit scale, it boils, freezes at 32 and boils at 212, right? Which is always, this is kind of one of those things where if you're always operating on the metric system, then, you hear the weather and they talk about that it's freezing outside, but they really mean it's 32, not 0, or, they're talking in, or the Fahrenheit scale is slightly different when they're talking about that it's, below 0 or whatever, and they're not really talking about degrees Celsius below 0. So the Kelvin scale is an absolute scale, okay, where There is no zero. By absolute means that there is no zero. Okay. There is a 0 Kelvin technically, but it's a theoretical value. Okay. We can't get to it. So in any of our chemistry that we need to do, we will generally work from the Kelvin scale. Okay. Now, the conversion between Celsius and Kelvin is we're just adding 273 or subtracting 273. So it makes it pretty easy. And the scale difference is the same here for both of these. So an increase of 10 degrees Celsius is also an increase of 10 degrees Kelvin. All right, so we already know that if we increase 10 degrees Celsius, that's not a 10-degree change in Fahrenheit, right? So, but it's a same degree wise, okay? But we're just adding 273 or subtracting 273. All right, so temperature is a measure of kinetic energy, okay? How much kinetic energy does something have? How fast is it moving around? So the more kinetic energy it has, the higher its temperature. Okay, so temperature is a function of kinetic energy. So time's an interesting unit, one we rarely think about. You know, we take for granted kind of things like the second, like how do we come up with the second? Obviously, we know like a meter and things like that for how wide they are, for how long they are. But how do we measure how long a second is? Like, is it counted like 1 second, 2 second, 3 second? Is it 1,000, 2 1,000, 3 1,000? Is it 1, 2, 3, 4? Like how long do we count for a second? And so the technical definition is looking at specific radiation events or transitions of cesium-133. And so we measure with the NIST, so National Institute of Standards and Technology, generally keeps the clock. So their current version is the NIST F2 cesium clock, which is so accurate it will not gain or lose a second for about 300 million years. It has an uncertainty, and we'll talk about uncertainty, is measured at 4.1 times 10 to the negative 16. So that is a whole bunch of zeros. Okay, that means their accuracy is incredibly finite. Okay, so we measure time going forward, but we can also measure that same kind of thing going backwards. So we measure cesium in its radiation events. We can also measure other kinds of radiation in time as well. So we have a variety of radiometric clocks. Okay, we have a whole periodic table of elements, and some of them are radioactive. And because of some of them are radioactive, we know things like the radioactivity of these elements are constant. So their radioactive decay are constant for the various elements. So you can see between rubidium, strontium, samarium, neodymium, lutetium, hafnium, uranium, lead. So most people are familiar with things like the uranium, lead, and things like that. Or you're familiar with carbon-13, right? So there are a whole bunch of these isotopes that exist naturally in us, in rocks, in all kinds of stuff. And so we can measure their decay patterns fairly accurately within the space in which each element operates. So each one of these operates within a different band of time. And so as we see kind of overlap, we can test between different clocks and validate between different clocks or different elements to see where their overlap is. And we can get pretty finite answers as far as how old certain things are. So uranium obviously has a half-life of about 7 million years, or uranium-238 has a half-life of 4.5 billion years. And so we can look at a whole bunch of various things. Now, we only use carbon really for things that are alive or have been alive, right? So this leads us to be able to tell things like the age of the Earth. So we know that the age of the Earth is 4.5 billion years. And we can tell this from these same isotopic decay patterns from a whole bunch of different elements. And one of the ways that we validate this, again, if we remember back to last night when I was talking about how do we collect evidence, how do we know things when we weren't there? So there's all kinds of evidence that we can collect. So just like when we're looking at the moon, okay, right? So the moon, we collected moon rocks. All right, so there's a question about the half-life. Well, I mean, we'll talk about half-lives probably later. It probably won't be something that we'll get into, at least probably not this semester. I mean, usually we talk about half-lives when we do kinetics in 112. So in 112 we spend a lot of time talking about kinetics, which is where we get things like half-life. You know, we can look at, you know, I can show you an example after the break if you want me to show you a picture of what it looks like. All right. So with the half-lives, because we know that they don't change, when we went to the moon and we brought back moon rock, okay, we also did dating of those same elements. Okay, you saw the mineral composition of the moon, and we have a mineral composition of the Earth. There are radioactive isotopes in those elements, and we can tell how old the moon is, and we can compare that to the Earth. So we already knew, right? So we just talked about the moon's formation, that something hit us, right? Something hit the Earth, and that spray and the spray of debris created the moon. So the moon, how old the moon is, how old that is when it formed, that means the Earth had to have existed at that same time or before that in order for something to hit us, right? There had to be something, the Earth had to exist in order for something to run into us, right? So if we know how old the moon is, then we also know within a period of time after that how old the Earth is in reference. The other thing that we know too is the moon doesn't have the same geology or tectonics, plate tectonics that the Earth has. One common thing is that we deal with is that the subduction plates, you know, things go back into the Earth. It recycles some of those elements, but it doesn't actually end up resetting a lot of those clocks. So, but there's places on the Earth that don't go back in, you know, don't have subduction zones. And so, but the moon is geologically inert. It doesn't have places where it's resetting some of the elemental clocks. So we can look at the moon. We have things like meteorites, right? We have meteor samples. And so we can date how old meteor samples are. So we can date back how old objects in our solar system would be, right? And so we can also look at other elements from other planets. We've looked at things like Mars. They can do isotopic analysis from Mars rock, from the rovers and things. And so we get all these little data points and we say, okay, well, these planets were created within roughly around the same time. And so we can begin to piece together how old our solar system is. And we can also look at our sun and put that together with other pieces of data. And then we get a fairly reliable idea of how old our planet is. Right? Some other ways that we look at radiometric data. So not specifically for dating the Earth, but there are other ways when we look at, if we're looking at, say, a fossil or say we have, you know, an archaeological dig that has unearthed some artifact, right? Some ceramic plate or pot, right? From Rome, from the Roman Empire or something, and we want to date it, right? So we can calibrate our instrument against other things that we also know with some reasonable accuracy, right? That's why we create standards, because we know how within some level of accuracy how old these other things are. Tree rings, okay? Now, trees are not a great way if you're trying to be super accurate, but they do provide a way to calibrate within some reasonable level of uncertainty how old something is, because the tree rings as it ages, it grows and has added rings. We see the same thing with coral. Coral has layers. And so we can look at a coral sample, a slicing of coral, and see its growth rings over time. And so we can validate things like the carbon content in a coral sample to how many rings it has, and then calibrate that against our instrument where we're dating things as well. We see the same thing in ice core samples. So the picture down here in the bottom here is an ice core sample. So when we take ice core samples from Antarctica, right, and they drill down, and we can look at the atmosphere at a certain period of time, and we get bands in here where there are trapped particles of gas. And so that's how we can determine what the atmosphere looked like 1,000,000 years ago. Because the rings or layers of sediment or of layers of gas trapped within the ice core sample correspond to the weather patterns of, you know, Antarctica's cycle, right? It snows every winter. We see snow every winter, another snow and another snow, and it creates layers just like the tree. And so they can date back how far back things are. And then we can look at what was the atmosphere like, because we can get little pockets, you know, when a snowflake hits down and it traps a little bit of air in there and freezes. Now we got little pockets of the atmosphere that they get trapped in there for millions of years. And so we can then calculate, what did the carbon dioxide content look like in the Triassic era? What did it look like in the Cretaceous era? Right? And so we can track atmospheric content along the same way. Okay. All right. So let's see if we can try this question here for real. I think this is our last one. So what is our SI unit? What is the base unit for mass? What is the base unit? What is the SI unit? Okay. So everybody's getting this one pretty well. There doesn't seem to be any other choices. I'm sure it's more than one person who just voted. Right. So yes, obviously the ounce is not it. The millimeter is a metric unit, but not a base unit for length. And the hertz, we will talk about. The hertz is a function of frequency that we will get to in one of the other chapters here coming up. But the only SI base unit identified here is the kilogram. If you think this is easy now, wait till I ask this like same question on the test, and people won't pick out the kilogram, right? All right. Okay, so this next section is a little bit difficult. I usually do this on the board. So this is kind of one of these things where I kind of usually will do this not like virtually. Usually I do practice problems and things to do this. All right, so what I'm going to do here real quick, just in case I can, 1 second. Okay, so when we talk about dimensional analysis, right, this is really kind of a way to keep track of units, okay, as we convert from one unit to another, right? One of the units that we'll first talk about is things like density, okay? So here density is more than one unit. It is a function of how much volume does a certain amount of mass have, right? So we look at things where they are more dense they tend to sink to the bottom, or they are less dense, then they float. So this is, the kind of chemistry that I do with my 5-year-old is, he calls it sink and float. And so we check to see, how, whether or not things will float in water and why they float in water, and the reason is because they are less dense. And so last night we talked about things like extensive properties. So again, this was that they are dependent on the quantity of stuff. Okay, but when we put mass and volume together, they become intensive properties, to where it is independent of how much stuff there is. Okay, solids we generally look at, so we're measuring mass divided by volume. Liquids we generally have grams per milliliter, but another thing you should recognize too is that a milliliter and a centimeter cubed are the same thing. So if you're given centimeters cubed, you can just swap it to milliliters if you need it. Okay. Gases, when we get to the gas chapter, we will see density in grams per liter. Generally, gases are much less dense, and so they need a little bit more stuff in order to have relevant mass. For most things, solids are more dense than liquids, solids are more dense than liquids, and which are more dense than their gases. The only exception is that of ice. Okay, so solid ice, solid water floats on top of liquid water. So in this case, the solid is less dense than the liquid. All right. Density is a physical property. So we talked about this last night, is where various pure substances will have a unique density. Okay, so iron, if it is pure iron, will have the same density as any other pure iron sample. Okay, but if we make a mixture of something, so water has a density of 1 gram per milliliter, but as we're going to find tomorrow when we look at the physical properties lab, as we add stuff to it, okay, and we put salt in there, that changes the density of the water. So a mixture, we can't really use as a pure, we can't use the physical property of a density on a solution to identify it, okay? Because a mixture can have various densities based on how much stuff we dissolve in it, okay? So the dimensional analysis really allows us, is really a way to keep track of the units, okay? We want to keep track of what units are going away as we do some various math. Now, for some of these early problems, it's a little over, it's a little too much for the first problems to do this way. But as we get into more complicated problems, the dimensional analysis helps us to keep track of our various units, right? It helps us to keep track of the units because we have a lot of different units. We're doing chemical reactions. We're changing something from one molecule to another molecule. We're going from mass to volume, and there's all kinds of changes that we need to keep track of, right? So the dimensional analysis helps us to keep track of what units are where and make sure that we're doing all of our multiplication and division in the right spot, okay? So what you'll see is when we have these problems, okay, when we have chemistry problems, we want to look at the easiest unit, okay? The simplest unit is generally where I would say you want to start, okay? So if we're told that, we work for 30 hours and we make $9 an hour, right? And we want to know how much are we going to make, right? 30 hours is 1 unit versus the $9 per hour is 2 units, dollars and hours. So you're not going to use the rate as your starting spot, okay? You're going to give the simplest unit your starting spot. The hours is a simpler unit, so that's where we're going to start, okay? And usually knowing where to start is sometimes the hardest part of some of the chemistry problems, right? If we can just figure out where do I start when I'm given a whole bunch of units, Right? That's usually our first problem, is when we have a word problem, we have a whole bunch of numbers that we're given in a word problem. How do I make sense of a bunch of stuff that's given to me? Where do I start with all this? Right? And so my suggestion would be try to find the simplest unit, as in the single term unit. Okay, start there, and then that usually will tell you what your first step is going to be. Okay. All right, so these are problems here. We'll look at some other practice problems here, but you can follow through these slides. All right. So what I'm going to do here is I'll all right. You guys can see my pad of paper, right? So let me stop, and I'm just going to go over here to this. Right. So you guys can see my recorded paper. All right. So you can't see this. All right. Let me. Okay. Should be able to see it. If you can't, right? I've got. Let's go to. Let me try to pin it again. Pin video, and we'll go to. All right. So. All right. Our question should be. All right. Everybody. Okay. You see it now? Okay, good. So, like I said, usually I do these kinds of practice problems up on the board. It's a little hard to do it here. I have to set up my phone, invite my phone as like, put it as another host, and then that way we can do this. Right? So in these kinds of practice problems, okay, the question here for some of this dimensional analysis might be, well, how many grams, I don't know, how many grams, right? How many grams do I have here? If I have 50 milligrams, how many grams is that? Okay. Now, this is a very simple problem, right? So this is where you would have your, so in this case, 50 is the only term I have, right? So it's easy to know where to start when it's the only term, okay? Here, this is where you would have your metric system memorized, okay? So I want to set my term opposite, all right? So this is going to help me to determine what is my next step? What do I do with this? So I want to put a unit of milligrams on the bottom here, okay? Because I want them to cancel each other. If I divide milligrams by milligrams, they cancel each other out, okay? So what I'm going to do is I'm going to put the top and bottom as equal to one another, okay? So for my metric system, I would say there is 1,000 milligrams in 1 gram, right? So I know that there's 1,000 milligrams in 1 gram, right? So I'm setting the top and bottom as my equal, okay? The milligrams cancel each other out. And so if I divide 50 by 1,000, so you multiply everything on the top and divide everything on the bottom. Okay. And so when we divide, so I get usually I would say this is where, you know, in class you would bring your calculator and we would work some practice problems, because sometimes I make these up a lot of the times on the fly, and so I don't have the answers, you know, set out, worked out all the way. So I have videos that I will post that I've been trying to do during the day of various practice problems. So I have time to kind of sit and do a 10, 15 minute of 2 or 3 practice problems and work my way through these. And so this is what the dimensional analysis looks like. Okay, so let's look at another problem here. Okay, let's say instead we have 3.1 meters cubed. And I want to know how many centimeters cubed is that, right? How many centimeters cubed are there in 3 meters cubed? Okay, so so this is the only unit I'm given. So this is where I'm going to start. Right? Now, I have a conversion where I know meters, right, and centimeters. Okay, that's something you would have memorized essentially from the metric system. In 1 meter, there are 100 centimeters. Okay, but a meter does not cancel with a meter cubed. So this is a linear unit. Okay, this is the linear unit. So I can turn my linear unit into a cube unit by cubing the whole thing. Okay. Now, can't hear me? I should be able to. Everything should be, maybe I'm getting too far away from my mic. Maybe that's because I'm leaning over trying to work the practice problem and not paying attention to where my mic is. Better now? All right, so we have 3 meters cubed. Okay, so we have 3.1 meters cubed, and we want to get to centimeters cubed, okay? We know from our metric system unit, where we would have memorized, that there in 1 meter, there is 100 centimeters, okay? This is a linear unit, and I want to convert this, and I'm going to cube the whole thing to make it a cubic unit, okay? Because if it's 100 centimeters in one direction, 100 centimeters this direction, and 100 centimeters this direction, becomes a meter cubed, right? So I'm just going to cube my linear unit in order to do the conversion. So when I do this, I get 100 cubed, centimeters cubed, cubed, right? Everything gets cubed, right? I cube everything. Now, obviously 1 cubed is just 1, right? So in 1 meter cubed, there is 100 cubed. So don't forget to do this part. So this is the part that like people often, we write it down, fine. Like everybody writes it out fine, but then we forget to actually do the cubed value, right? And so here, I now have the conversion of meters cubed to centimeters cubed. Okay, so it becomes 100 cubed. Okay, 100 cubed times 3.1, right? Usually I don't leave myself a lot of room here, right? So if I rewrite my unit here, it's going to be 3.1 times 10 to the 6th centimeters cubed is my answer. Okay, so we'll do another one here. All right, the key here is the unit, the linear unit is cubed. Okay. Let's take a look at another one here.
Professor?
Yes.
Sorry, can you just explain how you got like 10 to the 6th and like breaking it down to it
Sure.
being 3.1 versus like what happens to the 100, I guess? I'm just confused on that.
Okay. Part. All right. So let's take it back to that. Good question then. All right. Again, like I said, if I skip a step, just let me know. All right, so the 100 cubed, all right, 100 cubed, all right. So when you go to your calculator, all right, this is where in your calculator, you got to be able to make sure that you can use whatever calculator that you're familiar with on the test. The test doesn't have it's not like on the other like online tests where it has like a built-in calculator. So you kind of have to have your own calculator. All right, so you should be able to use your own calculator. So when we do 100 cubed, right? 100 cubed becomes 1 million, right? Everybody follow me on that one? So it's 1 million. 100 cubed is 1 million. Times, what did I say? It was 3.1? 3.1. Okay. And so in your calculator, you're going to get a number that looks like this. Right? 3-1 with 5 zeros. Okay. And so what I did here is then I converted this to scientific notation. Okay. So if I move the decimal place here, 1, 2, 3, 4, 5, 6 times. Okay. So that it becomes 3.1 times 10 to the 6th centimeters cubed.
Thank you.
Right, so 3.1 meters cubed. In 1 meter cubed, there was 1 million centimeters cubed. We multiply the numbers on the top, divide the numbers on the bottom, and we would have gotten a number like this on your calculator, and then we would convert to scientific notation, which is to put the decimal place in between the first two numbers, and however many places we move this way is positive. If we move this way, it becomes a negative exponent, right? All right, so let's look at another problem. Okay, we have okay, so this is a density, right? 4.11 grams per centimeter cubed is a density. Okay, now I want to convert this to some asinine US unit, pounds per cubic inch. Okay. So in this case, I would have to give you a conversion factor, right, of pounds and grams, right? So there are, let's say it's like 453. So there's 453.6 grams in 1 pound. Okay, so you would have to be given this unit, okay, 453.6 grams in 1 pound. We also know that there is 2.54 centimeters in 1 inch. Okay, so for the American units, you would have to be given these two. Okay, so for this one here, we don't have any other units, so we don't have a choice. This is not a, so if we had a simpler unit, that would be where we would start. But here I'm converting my density from grams per centimeter cubed to pounds per inch cubed. Okay, so here it doesn't matter which unit you want to start with. Okay, now I will probably here start with the grams. Okay, so I have a term of grams next. So I want to set the grams opposite. Okay, and I want to convert from the grams to something else. Okay, so in this case, I have a direct conversion of grams to pounds. Okay, again, my top and bottom are equal to one another, right? So there's 453.6 grams in 1 pound. Okay, so if I stopped right here, my grams, when I divided them, they go away. All right, if I stop right here, what is my unit? Pounds per centimeter cubed. Okay, but that's not what I want. I want pounds per inch cubed. Okay, so I have one more conversion to do. Okay, now here I want to set the centimeters opposite. Because the centimeters are on the bottom, I want to set my next centimeter unit on the top. Okay, I want them to be opposite one another. I'm going to convert from centimeters to inches. Okay, we know there are 2.54 centimeters in 1 inch. But centimeters cubed don't cancel with centimeters, right? That's a linear unit that doesn't cancel out fully with a volume unit. So I'm going to cube the whole conversion. Okay, so in your calculator, you're going to do 2.54 cubed, right? And so this is what it's going to look like then. All right, so let's rewrite this a little bit. 4.11.
We have a question.
Sure.
Why are you cubing it? I'm just confused about, like, when are you supposed to cube?
Well, you're going to cube it because 2.54 centimeters in an inch is a linear term. Okay.
Okay.
So this is 2.54 centimeters, right? But I want to go here and.
Okay.
Right.
Yeah.
My horrible, make me draw a horrible cube, right? So I want to make a cubic value, but each one of these is 2.54.
Okay.
Okay. So in the whole cube, everything has to get cubed. Now this only happens when we're talking about volume units. Okay. All right, so 2.54 cubed. So if you're doing this in your calculator, 2.54 cubed is 16.4 centimeters cubed. Okay. So this is my 2.54. So if you do, so in your calculator, 2.54 cubed, you should be down here to this. Okay. Now we can see by dividing my gram units by one another, they disappear. By multiplying and dividing my centimeters cubed, they disappear. So now the only two units left over are pounds per inch cubed. So I multiply all my numbers on the top, divide by all my numbers on the bottom. Okay. So when I do this, all right, so 16 times 4.11, I get about 67.3, and then divided by 453.6, I get a value here of 0.148 pounds per inch cubed. Okay. So like I said, these kinds of unit conversions, we will do more of these. I'll have other practice problem videos like these as well. All right. We can do one more if you want. well, let me get to the density, and then that way we can do a practice problem using the density, right? So let's. Okay, I guess I don't have any. Oh, okay, I guess I don't. All right, so let's just. All right, so let's just look at the density then. All right, since I didn't really have anything else in the PowerPoint for density. All right, so one of the kinds of conversions that we have to be able to do is to use density, right? So density, grams per centimeter cubed, right? So if we have, say, a density, okay, we had 4.11 grams per centimeter cubed. That was a density we used previously, okay? Density is mass divided by volume, right? So when we have a density, the density value is a conversion factor between mass and volume, okay? So it's not just a unit. The unit by itself, the power of these kinds of things is not simply the fact that it's a unit. It is the fact that it allows us to convert between other things, okay? So for example, let's say we have 50 grams, right? Let's say this is, say this is lead, okay? All right, PB, right, is lead. All right, you should probably start. All right, so I didn't quite make this probably very clear in the other day, but we're going to talk about nomenclature. Usually what I recommend for the 111 class is that you should probably know the first 30 elements, right? Or the first 20 elements, and then there's like another 10 or so that we'll get to here shortly. But I will use a variety of elements so that way you begin to get familiar with some of their use. All right. So PB is lead. All right. So we have 50 grams of lead, and let's say this is its density. Okay. My question here is, how many centimeters cubed of lead do I have? What is my volume of lead? Okay. What is the volume of lead? Okay, if I have 50 grams of lead, what should its volume be? Right? If you're not familiar, one of the ways that we would measure this, like if we're talking about like a rock, right? What we might do is volume displacement. So we would take right? So this would be like 10 milliliters here, right? And then we would take our object, right? And then we would place it into the water. And then as it goes into the water, it would raise up the volume. And so then the difference, okay, the change in volume, all right, one of the terms you're going to see later, okay, is this little triangle here, okay? The triangle means change, okay? It's the term delta, right? So it's delta V is the change. So we would measure the change in volume by putting an irregular object into a cup, right? We can look at the volume displaced, okay? So if I knew how much this weighed, 50 grams, right? So if I had my 50 gram lead and I put it in some water, the change in volume, I could take the 50 grams and divide it by its volume and know what its density is. Right? That's generally how we would measure an irregular object. Okay. Now, if we already have the density, then we don't really need to go through this in order to calculate its volume. Okay. We can calculate its volume with the density. Right. So we have the mass, we have the density. So we want to find the volume. Now, if we rearrange this equation, we get volume equals mass divided by density. Right? So we have mass and we have density. So we would divide the two, right? That's what our equation says. All right, but we're going to look at this from the dimensional analysis standpoint. 50 grams is a simpler unit than grams per centimeter cube. There is one term here versus two terms. One term is simpler than two terms. So 50 grams is where I'm going to start. Okay, start with your simplest term. The density here, okay, so I know I have to divide by my density. Okay, when I divide by my density, right, where does the volume go? The volume is up here. All right, let's look at this. If I do this, 4.11 grams for every 1 milliliter, right? Or 4.11 grams for every 1 centimeter cubed, right? So the gram is what I set opposite, but when you divide by a fraction, it's like multiplying by the reciprocal, right? So the gram is the denominator and the centimeters cubed gets flipped up to the top. And so when I divide grams by grams, what is the only unit that's left over? The centimeters cubed, which is the volume, which is what I wanted to know. This is also, so we already knew we had to do this. We already knew that I needed to take the 50 grams and divide it by the 4.11. We already knew that from this equation. The dimensional analysis is just showing what happens to the units. How do I get to the volume from that? Okay, how does dividing grams by grams per centimeter cubed give me a volume? This is how. Okay, because the gram units cancel out, leaving me with a volume unit. Okay, and so we do 50 divided by 4.11. All right, and I get 12.2 centimeters cubed. All right, let's look at another one. All right, shall we? Let's look at one more of these. All right, we're going to keep the same density. All right, still talking about a piece of lead. Okay, I don't even know if this is actually lead's density. I'm just making this up. All right, let's assume that we have 304 microliters of lead. How much does it weigh? In grams. Now this is kicking it up at zoom in. Okay, well. Problem is, how do I zoom in? It's not going to overdo it. I mean, you may have to make your screen a little bit bigger. That might be the only thing you can do, because I think I turn off my main video. So this should be the only thing you're seeing is the scrap of paper, right? It's the only camera that's on now. Can we read it a little bit better now? Or do I need to zoom in a little more? so that's about as big as I can get it without, you know, moving my page around too much. Oh, did I turn off the video? What happened? All right, are we back? You haven't seen the sheet at all. Yeah, so you got to look at Sam 67 is my other screen. So if you're maybe not watching the other screen, it's, you know, yeah, if you only have like one screen set up, you know, you have it like in presenter mode or something like that, you maybe just be looking at the one screen. So you may have to play with your settings a little bit. Yeah, there you go. Like I said, we got to kind of help each other out with figuring out how to be able to see everything. Like I said, they changed like 2 settings on Zoom, and it threw me off for like 3 days. So I probably should have made that clearer, that if you clicked on that I needed the other, because I mean I see my 2 screens. That's all I see. All right, so hopefully we're back to this. All right, now this is probably a harder problem. Okay, this is going to require some upfront calculations before we can even do our calculation, really. Okay, so we know again that density is mass divided by volume. So if we have the volume, we have the density, we don't have the mass. Okay, so if we rearrange our equation here, mass is going to be density times volume. Right? That should be what we end up doing. Now, in this case, it's not quite as simple as multiplying those two, because this is a microliter and that's a centimeter cubed. These are not the same unit. So we cannot just multiply our density. All right. So I might change this 4.11 grams per milliliter. Right. I would probably change this to that. Right. That way I'm working all within the same liquid unit.
On the exam, will it be the same unit?
I don't think you can count on that, because again, this is the type of conversion that you should be able to do. This includes this works in some of the metric unit conversions. This works in density conversions, possibly even dimension, some of the cubic units. And so this is a harder problem. Okay, this is a harder problem, but not something that is impossible that you shouldn't be able to do for the test. Okay, again, types of practice problems that I do are the types of practice problems I think you should be able to do, okay, by the time the test comes around. Now, obviously, you don't have a whole lot of time, so this is why we have to practice all the time. We have to be working on these problems, and that's why having the study guide is helpful to do, figure out how these problems are done. Okay, so let's look at how this problem is done. All right, again, I'm going to start with the simplest unit, my volume, the 304 microliter. Okay, now I can't just convert my other value, so I have to go from microliters to milliliters. All right, so this one requires either a little bit of dynamic thinking, okay, or we can do it the long way. Okay, again, it's entirely up to you. All right, let's just take it the long way, okay, and assume that we don't do the dynamic thinking just yet, right? So there are 10 to the 6th microliters in 1 liter, right? That would be the metric system unit that we would have memorized. There are 1 million microliters in 1 liter. There are 10 to the 6th microliters in 1 liter. And then in 1 liter, there are 1,000 milliliters. Okay, so this would change our volume unit into milliliters. Now you could do this all as one extension. It's just because I'm writing big, I don't leave myself a lot of space. So if I was writing in my normal handwriting, then I would probably make it small enough that I could do all of these calculations all in one row. All right. Okay. So I would multiply all the numbers on the top, divide by all the numbers on the bottom, right? So this is probably going to come out about 0.34. So 304 times 1,000 divided by 10 to the 6th. And so I end up with 0.304 milliliters. Right? Everybody should be able to follow me on that. Right? Now I have the volume unit where I would need it to where I can now use the density. Okay? So I'm multiplying by my density. So that means that the 4.11 grams per milliliter is what that looks like in the dimensional analysis. We already know we have to multiply these two together. Okay? The dimensional analysis just tells us what happens to the units. The milliliters cancel each other out. 0.304 times 4.11 grams tells me that I have 1.25 grams. All right, I'm going to write this one more time. Okay, I'm going to write this from start to finish in kind of the little bit more kind of dynamic thinking here. Okay, 304 microliters. Okay, there's 1,000 microliters in 1 milliliter. Okay, so this is the slightly more dynamic thinking here that we would have to apply to the metric system, right? So this is 10 to the 3rd, right? 1,000 is 10 to the 3rd, 10 to the 6th. So if I get rid of the 10 to the 3rd and 10 to the 3rd, right? In 1 milliliter, there's 1,000 microliters. Again, you don't have to be able to do that. That's just once you do enough of the metric system units, we should be able to make those kinds of logical steps, right? So my 304 microliters times 4.11 divided by 1,000 would give me my 1.25. Okay, so like I said, so this one in particular is a little harder. Okay, it's a little harder because it has the extra step in there. little extra dynamic that you have to deal with. All right. So what I'll probably do is tomorrow when we look at this. So let me just take a quick look at the last bit of the chapter here, because it's just all right, so everybody, we should be back to the PowerPoint, because really the last thing that we have to deal with are significant figures. It's fairly simple concept here, but we'll use this in some practice problems. And what I'll do is I'll post some practice problem videos that deal with the combination of these various things tomorrow. So significant figures just deal with when I was putting stuff in my calculator, okay, when I'm dealing with all of those calculations, how did I come up with the right number, right? When I'm multiplying by 1,000,000 and I have a whole bunch of digits, how many of those digits do I need to write down? Okay, when I picked and rounded some and said it was 4.2 or 1.25, why did I pick 1.25 instead of 1.2, 498,217 that my calculator said, right? So significant digits are a way of representing what is accurate in our values. Okay, so when we take measurements, we look at qualitative and quantitative measurements. Okay, so qualitative are really just how something appears. So in one of the labs that we would normally do if we were meeting in person is a solubility lab, where we take stuff and we mix them together and we look for color changes and we look for where solids are being made. And we can tell we're just making visual inspection of the things. But so there's no numerical value that's there, okay? Versus quantitative measurements are numerical value. So we would put something on an instrument. We get a reading on something and we have a number value. Okay. So when we look at values, when we do things in the lab, we have various things like accuracy and precision that we have to be concerned with. Accuracy deals with how close something is to the actual value. So if I'm measuring density, so like we'll talk about this in our physical properties lab. If you are telling me that the density of water in 5 samples is 21 grams per mole or 21 grams per milliliter, well, that's not accurate because the actual density of water is 1 gram per milliliter. Okay. But your values might be precise because all of your data is similar to one another. You did 5 samples of water and all 5 samples came out at 21 grams per milliliter. Okay, so precision is about how close the data is to one another. Accuracy is about how close it is to the actual value. Okay, so in a diagram form. Okay, so in A, where all of the darts are next to one another, but they're not on the bullseye, they are considered precise. B, they are both precise and accurate because they are all on the center dot where you wanted to hit them. And then C is random. Okay, so when we do significant figures, okay, these are a bunch of rules and you can read over these and we'll look at some practice problems probably next time where we'll go over these in more detail. Okay, so really here we're looking at various digits, which ones in a calculation are important, which ones are not. Okay, so essentially any non-zero numbers are going to be significant. Really, the one key here is the leading zeros. So number 3, leading zeros are not significant. So when we have these various digits, so as you convert that number into scientific notation, okay, the 0.0100105, those front zeros disappear. So if they were significant, then they wouldn't have disappeared. But leading zeros are not significant. Okay, so we want to be able to count how many digits are important when we do a calculation. Okay, exact numbers we don't count, or we don't count things like the metric system conversions, because we're going to consider those to be exact numbers. Okay, so exact numbers are infinitely accurate. Okay. So here the question is just really how many significant figures, how many significant digits are there in each one of these? Okay, so in A, the leading zeros are not significant, so it's only the 2 and the 0. So it's 2. In B, all of those numbers are significant because anything after the first real number is significant. In C, all of those are important because even zeros that are in between two numbers are considered significant. Right? So A has 2 significant digits, really. B has 4, C has 5, and D really is kind of ambiguous where it has 1. Right? Now, when we use these, our concern is going to be when we multiply and divide. We're going to do a lot of multiplication and division, so that's usually primarily where our concern of what sig figs are important. So when we take numbers and we multiply them by one another, okay, the least significant measurement is driving our accuracy. Okay, just like the saying goes, a chain is only as strong as its weakest link. Okay, a relay, race is only as fast as its slowest runner. A unit of measurement is only as accurate as the least accurate term. Okay, if I take a 10 milliliter graduated cylinder that has 2 decimal places of accuracy and I throw that into a swimming pool, it doesn't matter. Okay, that accuracy is totally lost on the 1,000 gallons that I have in there in my pool. Okay, it is absolutely irrelevant because the least accurate term dominates. Okay, so this is why when we are doing various kinds of measurements in the lab, we want to make sure that all of our terms are as accurate as possible and using the most amount of accuracy as we can get, because when we do combine these various things, we end up limiting our accuracy by the one step that we took that was sloppy. Okay, the one inaccurate term by pouring it into a beaker. Okay, when we mixed everything together in a beaker, we lost the accuracy from our analytical scale. We lost the accuracy from our graduated cylinder. Okay, so the least accurate term drives the answer. So, all right. So, in this case, the fewer number of significant figures is going to be our indicator of which one is the least accurate term. Okay, less significant figures means less accurate. 2 significant figures is less accurate than 5 significant figures. So when I multiply these two together, my answer is going to have the same number. One second. Dog was eating the attendance sheet. I'm sure whoever's name that was will still count you there. All right. So when we do the multiplication, the least accurate term, 2 digits, my answer is therefore going to have 2 significant figures. Okay. When we do addition and subtraction, it's not based on the number of significant figures, it's based on the number of decimal places. Okay. So the fewer decimal places drives the answer. Okay. When I add 15.152, 1.76, and 7.1, 1 decimal place is the least accurate term. So therefore my answer has 1 decimal place. Okay, so it's 24.0, right? So it is the number of decimal places that drives the answer, right? Now, obviously after the first quiz, okay, the first quiz, there's going to be questions on significant figures. But after that, the tests are already going to have the right number of sig figs. So this is kind of a, this will be rendered mostly moot after this. And since we're not in the lab taking measurements, again, it's kind of something that kind of gets rendered moot. I usually, I harp on significant figures because we're in the lab doing experiments and there's glassware and analytical tools that we're using that people should be paying attention to the sig figs on. Okay. But since we're not actually doing any of that, this will kind of fall off really after the first quiz. Okay. All right. And so we have some other things where we have some mixed units. Again, order of operation kind of things apply. All right. So, when we do the subtraction here, the 2 decimal places, the answer will have the 2 decimal places, and this will drive the fact that there are only then 2 sig figs versus the 4 sig figs. So the answer will therefore have 2 significant figures. Okay. We'll spend some more time working on these kinds of problems a little bit later. So you can kind of look at these slides and then, try to make sense of it. And then we'll come back and we'll work on some practice problems from these, and I'll do another video on this as well. So I have 2 videos that I'll probably do tomorrow. One is another units and another sig figs. I did 1 sig fig video today, so I'll post that up. All right, but I only did like 3 problems. So I try to keep the practice problem videos short, so that way they don't lag on for too long, because this is going to be a long video to post. All right. So I'm going to call that where we'll end up for the night.